the Q&A part of the discussion. Now I can share my screen, which I will do. And I see that David and Petros have actually answered some of the questions that were, or maybe all of the questions that were asked them, on Slack, or in David's case, as he mentioned, Joachim, his student, has answered them. But so actually, so thank you, David, Mary, and Petros, Lydia, for hanging on to answer some of these questions. David, I was wondering, and I didn't have a chance to put it on Slack. So the usual issue about blockchain is, using up terawatts of electricity, because the miners need to solve this particular kind of funny, useless task. Your work is sort of independent of the question of how the mining will be done. Is that correct?
Yes, correct. Let me elaborate a little bit on that point, which is important. So the original, by the way, can people hear me? Yes. Okay, great. It's pretty bad talking for 5 minutes and nobody can hear you.
Yeah.
So the original Nakamoto's protocol is based on proof of work, which is consuming tons of energy. But since then, many people have derived versions of its protocol, which is the same longest chain protocol, but for using other resource, which is not environmentally more suitable. For example, using stake, in other words, how much stake you have in the system, or using space, proof of space, and so forth. So what I talk about is that we have this longest chain protocol, which keeps on growing like ever-ready bunny, and that holds regardless of what resource you use to do the sort of lottery to generate the next block. Does that answer your question, Ken?
Yeah, thank you. Yeah. So I'll try to have some kind of general questions to this afternoon's speakers, but I think the next thing would be to walk through the specific questions for Mary, since David's questions to David have already been answered.
So before Ken, before you go to
sure.
Mary, maybe I can take one of these questions that was asked and elaborate a little bit more on that. I think it's important.
Oh, absolutely. Sure.
So the question that John Smolin asked was, why do I consider Bitcoin as a synchronous assumption, right? Why is it synchronous assumption? So if you think about Nakamoto's design, he designed the block generation rate to be 1 block every 10 minutes. So that's very slow. That is essentially chosen to make the protocol synchronous, even though the delay could be up to like a minute. So the important thing is not the absolute length of the delay, which is long because you're in the internet or across the world, but the more important thing is sort of how fast the block generation rate is compared to that delay. And by making that very long, he essentially convert the problem into a synchronous problem. So that's all I want to say. So please,
okay.
Because that's an important point, and it's a point of confusion in many studies of this problem.
Okay. Thank you. So now, just looking at the questions to Mary about her talk, one of them from John Siddles is sort of an average case versus worst case kind of question, that suppose you are in a situation in which you have the coefficients distributed according to Benford's law, then can you still make the sort of no information argument about not being able to do the reconstruction? I don't know, Mary, or if you're there.
Yeah, I'm here.
Okay.
Interesting question. Yeah, sorry that I didn't realize that I could have been answering these questions on Slack to save us some time, but I guess I can.
Well, it's all good. I mean, it's fine. I mean, I think that they're of general interest, and it's worth having a discussion about it, as well as as well as a Slack interaction. So
yeah, so
both are good.
Yeah, I mean, so this is a really good question. So I guess the question, just to rephrase it, is like what we sort of talked about during my talk was like, if you get less information in terms of like, let's say I only get 2 points instead of the 3 that I need to recover a quadratic polynomial, like you couldn't learn anything about a 3rd point, assuming you don't know anything about the underlying polynomial. But the question is like, what happens if you think that this underlying polynomial comes from some particular distribution that is not uniform over all of the polynomials? What could you do then? That's actually a really good question, and I don't know the answer. I guess typically in applications, you'd think that like, so the coefficients of the polynomial are basically like the message, which you think of as already have been like compressed down to the case where it's just like uniformly random. So in applications, you would think that you would not have such a strong prior. But I could also imagine applications where like maybe your compression isn't so good, or if it's coming from other situations where you would have a strong prior over your message. And in that case, yeah, it does seem possible that you could do better. And I have not thought about that. It's a really good question.
Okay. So John Smolin asks if fun fact 2 can be expressed as a result on error correcting Reed-Solomon codes, or is it a generalization or error correction to some more complicated situation?
Oh, that's a really good question. So fun fact 2, to recall, was this low bandwidth interpolation for polynomials. Yeah, so it actually is part of like a much more general phenomenon. So I've phrased it for Reed-Solomon codes because everyone loves polynomials and it makes sort of a good high level talk. But it actually works. The framework in that paper that I linked to is a paper by myself and Venkat Guruswamy from 2017. We actually give a much more general framework that works not just for Reed-Solomon codes, but for basically any linear code over a big enough field. And basically being able to do this boils down to the dual code having like particularly nice properties. Basically, you want to be able to find a set of, I'm using some technical jargon here, so I hope that's okay. Like, being able to find a set of dual code words that obey certain properties. In particular, if you're viewing your field f2 to the t as a vector space over f2, if you look at these code words, you want this sort of symbol by symbol, like the dimension of those symbols as elements of the vector space over f2 need to be nice. But so it's a very general condition that works for linear codes in general. For Reed-Solomon codes in particular, the dual of a Reed-Solomon code is also a Reed-Solomon code, so it just all becomes computations about polynomials. It becomes really nice. But yeah, it's just much more general.
Okay, so Ilya Neminin asks if you could use, in particular, Fourier polynomials or orthogonal algebraic polynomials, and whether that would be helpful in terms of the amount of data that's needed.
That's a good question. So I guess this is actually similar to the first question that was asked, because this is like saying if I restrict the space of polynomials that I'm looking at, can I learn something more? And the answer is probably yes, but then on the other hand, you've restricted the space of polynomials that you're looking at, so you're not going to be able to pack as much information into them from a coding perspective. So yeah, it's a good question. I haven't thought about it. It's the same answer as I guess to the first question. I haven't thought about it. Maybe you can, but your data rate's going to suffer if you were to do that.
Okay, I think the next question by John Smolin was answered by Chai Hua. I could be wrong. Charles Bennett asks if you can asymptotically recover full information about a missing byte by taking an 8 plus epsilon bit hash of all of the surviving file fragments.
Yeah, that's a good question. So I guess the setup would be like, I have this piece of information that I want. I know that somehow it's available in the thing that, in the information that's left. If I just like take a random hash or something, can I get that data out? Turns out actually no. So there are some settings, like some parameter regimes, where even though I only want to recover 8 bits, I actually provably need like significantly more than 8 bits in order to do it. This is just a property of polynomials. So in some parameter regimes, yeah, like no scheme can do it. In particular, not taking random hashes. but there are other parameter regimes where it is possible to recover the 8 bits that you want from 8 plus epsilon bits on average. And those schemes are super algebraic. They're not. Sorry, these are schemes due to Tamo, Ye, and Barg from 2018, I think.
Is super algebraic a term of art or just meaning very algebraic?
Very algebraic, sorry. Yeah, no, they are extremely algebraic, as opposed to having transcended algebra, which I guess would be the other way to interpret it. Yeah, no, they're extremely algebraic, and in particular, they're extremely structured. And I think that even though in that case it is information theoretically possible to recover what you're after, these 8 bits from 8 plus epsilon bits-ish, I think if you were to take a random function, like a hash function or something like that, it wouldn't be able to do it. There's like this really precise structure that you're trying to exploit, and my intuition that is that like random hashes aren't going to do it. But yeah, it's a good question. Does that answer the question?
Well, Charlie?
Yeah. Yeah.
Okay.
Oh, yeah, I have another question right after, yeah.
Oh, you have another question, Charlie?
Yeah. Well, this was about conic sections. When
go
I
ahead.
learned about conic sections in high school, I naturally thought an ellipse is what you get by cutting a cylinder at a diagonal angle. But I was really surprised that it would be what you get by cutting a cone, because the cutting plane is not very symmetric compared to the cone, and one end is fatter than the other. So I thought it would be egg-shaped, but it comes out to be exactly elliptical. So the two ends are the same shape, but for different reasons. And I wonder if that had anything to do with where the axis of the cone falls compared to where the focal points of the ellipse are. Does it go,
a good question.
the axis of the cone
really
go through one of the focal points of the ellipse, or doesn't go, as it goes between them, not through either focal point?
I think I'd have to sit down and draw.
I guess
the answer to this question is that like you are exactly as equipped to answer that question as I am. So I guess I was drawing all these pictures of like taking sections of paraboloids and stuff, but actually like in this work, these are all things that are happening over finite fields. So the geometric intuition is just like out the window. So yeah, I don't know the answer.
But you remember, I mean, you've been to high school more recently than I do. You remember the cone with all these slices, and you cut it at this funny diagonal angle, and yet the cut is a perfect ellipse.
Yeah, I agree. It seems completely magical, but I don't have a good intuitive explanation. Maybe one of the other panelists here who thinks more about the real numbers does.
Well, don't ask Eilberger.
Right. So John Smolin, if you have a sequence of questions in Slack, but I can't quite make out if the questions were subsequently answered. So if you want to, and I think you can chime in if you're still on the call. If you want to do that, please feel free to. So
remember what I asked.
I think I see some of these questions. I realize looking at them now that I think this was just a confusion in my slides that I wasn't clear. I think the question was like, if you're choosing arbitrary evaluation points and just evaluating it on a this set by this set grid, how do you know that there's a line in that set? And the answer is you don't. I meant to say you're taking the full grid, so all the evaluation points on both axes.
But if I'm given 3 random points, is that not enough to reconstruct the 4th one?
Right. 3 random points, I think, are not enough.
Well, they definitely are if they're on a line.
Yeah, for sure they are if they're on a line. Yeah, I think. Yeah, I'm not sure off the top of my head. I don't think 3 random points are enough. But don't hold me. I guess this is being recorded. That'd be embarrassing if I get it wrong. I don't think it's enough. Yeah, and I apologize for the confusion on my slides. I meant that you're sort of taking the full field on each axis, so you have sort of the full evaluation grid.
Okay. Well, my next question was, you were talking about the higher order polynomials wrapping around in a funny way
Mhm.
and things canceling out. Is this an aliasing effect or is it something different?
I think
Whenever I hear wrapping around, I think aliasing.
right. I think this is not an aliasing, or I guess it depends what you mean by aliasing. This is like just a sort of an algebra fact. Like, so when you're working over a finite field, like, so one example of a finite field, not the one that I was talking about in this talk, but one that's sort of easier to think about is just the integers mod a prime. And so, those things wrap around, if I add 3 plus 4 mod 5, I get 2. In some sense, it's wrapped around. And you also get this sort of funny behavior in a finite field when you start powering things up. Eventually, it wraps back around to the beginning. Like in F256, if I take x and then x squared and then x cubed and then keep going, by the time I get up to x to the 256, I've gotten back to x again. And it just sort of goes around and around and around. So that's sort of what's happening in the finite field, is that at least multiplicatively, you always sort of have this wrapping around thing. And then additively, like when you add stuff to itself, it cancels in funny ways. So maybe you could call that aliasing if you want. But yeah, it's just sort of a property of how finite fields work.
I think that would qualify as a non-fun fact.
I think it's morally. It sounds morally like aliasing to me, but
yeah, perhaps. Yeah. I guess
so,
the cyclic thing is aliasing when you're doing it in like a finite field of characteristic 2. Then it's not really wrapping around in a cyclic way. It's kind of like funnier, but maybe it's a fancy way of saying aliasing.
Fine.
Yeah.
But let me ask you, what is the multiplication rule you're talking about that isn't multiplication mod 256?
Oh yeah. So if you haven't seen this before, it's a little bit complicated to explain, but I'll just say the high level thing. Like, so to construct a finite field of size 256, basically you have all these bit strings. What you want to do is you want to view those bit strings themselves as polynomials, where each of the bits are like coefficients, and then you're going to multiply those two polynomials together. Basically, you're going to do polynomial multiplication, and that will give you some other polynomial. But like, oh no, now it's too long. Now it might have degree bigger than 8 or 7 or whatever your original thing did. So you have to somehow reduce that mod some other polynomial to get back to a degree 8 bit string. So if you choose the polynomial by which you reduce by cleverly, you can show that this multiplication rule turns out to obey all of the nice laws of algebra that you're used to. This is called a finite field. Yeah.
So it's like a convolution of these two strings?
Yeah, it's like, take a convolution and then take it mod some other polynomial.
Okay.
Yeah.
Okay, I think there's a few sort of quick kind of questions perhaps. So Vikesh Sidhu asks if this polynomial-based encoding decoding scheme works for error models other than erasure.
It does. Yes.
It does.
So this is not true even of the sort of the newer facts, but even like the classical things, classical Reed-Solomon codes. One of the reasons they're so powerful is they actually work for example, for errors as well. Like if one symbol gets changed to a completely different symbol, then it turns out that there are still efficient algorithms to do noisy polynomial interpolation. So if you have most of the points on a parabola and a few of them are a little bit off, you can sort of correct that and figure out what the parabola is. So they do work and they're efficient algorithms to do it, and it's really pretty and great. Reed-Solomon codes, awesome.
Awesome stuff. So another question from Vikesh is if they achieve capacity.
So that's a good question. So I guess achieve capacity generally means achieve capacity on some channel. So like on the binary symmetric channel or something like that. So for Reed-Solomon codes, asking if they achieve capacity on a fixed channel doesn't make a lot of sense, because as the code length grows, so does the alphabet size. So it's not just one channel, it's like the channel is changing. But Reed-Solomon codes do achieve sort of the best trade-off between rate and distance that is possible. So in that sense, they achieve some kind of capacity. Reed-Muller codes, these are the multivariate versions. Those you can have over a fixed alphabet size, and those it was very recently shown in a big result that those do achieve capacity on the binary erasure channel. I believe it's still open whether or not they achieve capacity on the binary symmetric channel for all parameter regimes. although there's been some work on that in particular parameter regimes. So more things we don't know about polynomials.
Okay.
Is the Urbank result?
Hmm?
You talking about the Urbank result?
Yes. Yeah, I should remember the
That's
author.
quite a few years. Actually, that's quite a few years ago.
Yeah.
That was 5 years ago.
5 years ago, was it? Time flies. Okay. Yeah, fair enough. It felt recent to me.
That was the Simons Institute program.
Yeah, that's right.
Yeah, that's not a perspective you should have somehow, but okay.
Well, I guess it's like in the life of this problem, the problem was open for like 50 years, right? So 5 years ago was still pretty,
fair enough.
Yeah, and as David said, it was
True.
solved by a bunch of people at a program at the Simons Institute, which I believe David helped to organize. So maybe that's his. He can claim credit for the result.
Okay. So Rupai Zhu asks a couple questions. So references the Razgraf-Smolensky bounds for relating low-degree polynomials over finite fields to low-depth circuits. So the question is, are there any circuit lower bounds results known for coding theory, kind of exploiting that connection?
Hang on, let me just read this question here.
Yeah, maybe.
I see. So the question is, low-degree polynomials over finite fields can be closely approximated by low-depth circuits. So are there circuit lower bounds known for coding theory? I guess in the sense that I'm trying to like think of like what such a bound would say. Certainly coding theory is useful in proving stuff about circuit complexity, although I'm not an expert on that. But I guess if Rupai is still here, like what sort of statement did you have in mind?
So there's he or she may not be able to speak because of the way that WebEx events is structured.
Okay.
So
well, if they're still here, if they can put in the Slack like
that's true.
What sort of statement they had in mind, that would be useful.
And there they are.
AC0.
Okay.
But like what types of statements for AC0 or?
Okay.
Maybe we can come back to it once. Yeah, sorry that I don't understand exactly what the question is. I'm probably just being slow.
So they have a second question about Newton polytopes.
Oh, I see.
So is that something you have a comment on? So if you use Newton polytope to represent the degrees of polynomials, are there polyhedral properties helpful to get more intuitive answers? So use Newton polytope techniques in this setting, I guess.
To more intuitive answers to like why is it that there are these like I guess funky high degree multivariate polynomials that restrict to parabolas or something like that.
I would think so. Yeah.
It could be. There might be ways to use polyhedral properties to get more intuitive answers. I don't really know much about this, and I don't know offhand the answer to this. Yeah, I'm not sure.
Okay, fair enough. So John, and if you want to chime in, John, please, Jonathan Leinster, please chime in. So his question is, in describing low bandwidth multi-point recovery schemes, you emphasize that the prime in the p to the t has for f sub p to the t has to be low order. Two questions: what is low in this context, and why use any p other than 2?
Right. So low can mean anything, but basically for the schemes that we have, things get better as t gets bigger, in some cases provably so. So the bigger t is, the better things are. So p can really be whatever you want, but then t needs to get large. So that means that your final field size is going to get large, and the larger p is, the larger t is. Why use anything other than 2? There's actually some constructions. Oh wait, hang on. Yeah, why use anything other than 2? That is a good question. One answer is just like, well, it works for primes other than 2, so why not? But yeah, I think I don't know of any compelling reason to use anything other than 2, although it might be that there are some things you could do over larger characteristics that you can't do over F2, but I don't know of any such examples.
There's some kind of trade-off involving the degree of something that would be, I mean, well, okay.
Yeah, or like
I'm just guessing what a possibility might be. Yeah, yeah. Okay.
Yeah. But you could imagine that, like, I don't know, maybe something funny happened, like when playing around with these sorts of constructions, like I was saying earlier, to the question about whether like random hashes would do well, there's like a lot of very specific algebraic structure that you're sort of taking advantage of in these constructions. And, you know, the algebraic structure over p = 5 is different than the algebraic structure over p = 2. Maybe there's some special thing you could take advantage of there. I don't know. But yeah, I don't know of any good reason not to use 2. But
okay,
I mean, there's not one.
Okay, so I just want to, so one last question from Chaiwa, is the low bandwidth recovery related to oversampled quantization and sigma delta modulation?
It's a good question. I guess it's related in kind of like at a high level way of sort of like where, in some sense, yeah, quantizing while oversampling, like quantizing, like we're looking at fewer, you know, less fine-grained information. So in that sense, it's related. In terms of the actual technical tools, because that stuff tends to happen like over the reals, and you know, the math there tends to be, you know, more analytical, and here the math is much more algebraic. I don't see any direct parallels, like, yeah, between the math in these two settings, but certainly, like at a high level, they do seem reminiscent. So
well,
maybe sorry.
Oh well, for the oversample quantization, there is a difference between linear decoders and nonlinear decoders. So maybe there's. Yeah, I wonder if there's something related to that as well.
Yeah, maybe so. Yeah, I don't know. I have to look into that. It's a good question.
Okay, so thanks, Mary. I think I'll move on to Lydia, actually, because if Petros, if you answered the Slack questions in Slack, then maybe we'll just walk through a few questions for Lydia. Yeah, so this it seemed like, Lydia, your talk seemed like there ought to be lots of, you know, deep philosophical questions there, and I have some vague ones having to do with the sort of the question of, well, somehow it ought to be related to the given that it's information theoretic, you know, can it be related to the information bottleneck framework in some fashion? You know, just throwing that out there. I believe Natalie Tishby actually has some results about proving generalization in the information bottleneck context. So it's not so crazy a question, I hope.
No, I don't think it's a crazy question. I think you're right that there's many connections that could be made, and I really wish we had a deeper understanding of these things. Even pack-based bounds, like I mentioned, I think there's a deep connection there, and we just, no one has really, I think, as far as I know, really pinpointed this connection. So yeah, I think the information bottleneck framework must be related, but it seems hard to argue about it. I think it seems a bit orthogonal. I think it uses, right, it uses right, the internal points of the classifier as the algorithm goes ahead. Sorry, not internal points, like internal steps as the algorithm moves ahead. And I don't really know how to connect it. I think it is slightly orthogonal. Like it's about how much, what's the fewer amount of information you can keep from random variable X if you want to know everything about Y, right? I think it's not obvious how CMI could be connected to that. What I want to say is that it's one of the connections that I feel is harder to make ultimately. I think there's other things that might be closer. But sorry, yeah. this is
okay.
But I don't know.
Maybe I'll skip to Srinivasan's questions. One of which is there a way to understand the CMI of an algorithm when it is allowed to make membership queries instead of just obtaining examples? Where it is allowed to make membership queries instead of just obtaining examples.
So what I can say about, I think that's a very nice question. What I can say about this is that there's a nice intuitive way to think about CMI, which says that if I have CMI, say, in the order of epsilon n, right? So remember, CMI is between 0 and n, so it's like having an epsilon portion of that. If my CMI is epsilon times n, then if I see the supersample and I see the output of the algorithm, then the probability that an adversary figures out the selector function, figures out the membership in the real sample correctly, is at least 1 minus epsilon. So if the CMI is high, then the probability that an adversary figures out the selector function, or like the membership of a sample in the real sample correctly, then this probability is high. If the CMI is low or 0, then with probability 1, they can't figure out membership. Now, I'm not 100% sure how this translates to the question, but I think it's the closest I can get. Right. So yes, I'm not sure. I'm not 100% sure how this algorithm that only is allowed to make membership queries would work, but yes, this is the relation that we have. CMI of epsilon n means that the probability that you figure out the membership of all these points in the real sample is at least 1 minus epsilon. So that's the quantification, the quantified statement. Now, yes, there is a relationship with the membership attack problem and these things. So this is what it boils down to, I think.
Okay, so Srinivasan has another question, which is if the techniques work for real valued functions, so you could get generalization bounds in terms of fat shattering dimension.
That's a nice question. That's a good one. That's a good one.
Okay.
Let's see. So my answer is the following. The techniques that we use for VC dimension, for classification, it boils down to saying that the amount of labelings of the supersample is bounded because of the VC dimension. And so this means that the amount of outputs, the size of the possible outputs of the algorithm, that's of the empirical risk minimizer, is also bounded by sort of the number of possible labelings of the supersample. And so it's an argument about how many about the size of the output space. And then the bound follows from just the Shannon entropy, and the CMI is bounded by the Shannon entropy of the output, and that's log of the output space. So that's how the VC bound comes in. I think, right, so the fat shattering dimension should also imply a bound on the number of possible functions that we could output that are consistent, sort of the possible labelings, quote unquote, with the supersample. I think, right, because of the covering number and its connections with the covering number, it's like 1 over gamma to the fat shattering dimension. So my intuition is that you could use the same kinds of arguments to say that the fat shattering dimension bounds the number of possible quote unquote labelings of the supersample, and this bounds the number of possible outputs of the algorithm, which bounds to CMI. So my intuition is that you could do that with a fat shattering dimension, but we haven't tried it. The proof is heavily based on the fact that quantum connections. Wow, yes. So the proof is heavily based on the fact of this counting the number of labelings, bounding the number of labelings.
Okay, great. So just one more. I think one more kind of question here would be, I think basically a little confusion of mine and of Ishan's about the global consistency property that. Well, from my perspective, I don't quite understand. It doesn't seem natural to me, which leads me to suspect that I don't really kind of understand the situation well, right? Why wouldn't more data imply that your hypothesis would shift a little bit or something? So I might miss something basic about it, I think.
Right. So that's a constraint that we put on the empirical risk minimization algorithm. So we're saying. Not every empirical risk minimization algorithm for a VC class has low CMI, but if our empirical risk minimization algorithm satisfies this property, then it has low CMI. So this property, okay, so I think I'm going to answer Ishan's question first, saying that the question is, how does the global consistency property help you avoid tie breaking? Again, what is the property? It's saying that if I have a bunch of examples and labels, and the algorithm based on these examples and labels gives me hypothesis H, then if I augment this data set or not, I don't have to augment it with more points. But if I label all these points, either the augmented ones or the ones I used to have, with respect to H, if everything corresponds to the labels that H would give to the examples, then the algorithm should still output H. So this is the key point, that if it used to output H and now you make everything consistent with H, it has no reason to switch to another hypothesis. And this helps with tie breaking because it's essentially saying, right, it's always going to output H if I give it these examples and labels. Okay,
so even if there was another hypothesis that was equally good, if it decided that it was outputting H, it's committed to outputting H.
It's very non-computationally efficient. The way to think about it is that you have an ordering, and you go with the first hypothesis that minimizes the error, and it's first in the ordering. So this thing always is empirical risk minimizer and satisfies this property. But yes, this is the way to make sure that the property holds.
Okay.
And yes, and thank you for your questions as well. I think they're good questions. It's hard to connect like information bottleneck and so on, but yeah, maybe if I can say something about this, your other question about the if and only if relation.
Okay, I think we're at the top of the hour, so it's
sorry.
So I don't want to.
Thank you so much. I just want to say thanks for the questions.
Yeah. So thank you for speaking. So one more time, let me thank all of the speakers, both for their beautiful, very accessible and interesting talks, and for a certain amount of patience with the format that we have here this afternoon to kind of helps pack things together a little more efficiently in terms of the time. And I would encourage people in both directions to ask questions on the Slack channel, and hopefully if the speakers want to kind of have a further look at the Slack channel, maybe there can be some continuing conversations there. And Lydia, if you want to answer my question on the Slack channel, I would be grateful if you would do that. But I think we can call it a day, and we'll restart the workshop tomorrow.